Hi friends, welcome to lecture 67 on our helicopter dynamics course. Today we are going to talk about rigid blade flap lag coupled motion, and now we are going to use some of the information about Coriolis forces which we discussed in the previous slide. I'm Dr. Ranjan Ganguly. Now here we are considering a rigid blade which essentially has flap and lag motions. And for simplicity of the equations, we will let the flap and lag hinges be at the same place, so we can use the same E value for all the equations. Remember that E is the distance between the root or the center of rotation and the hinge. So here the flap and lag hinge have the same distance from the root. Now this rigid flap lag model is pretty good for a typical articulated blade which has a large torsional frequency. So effectively, if the torsion mode is relatively stiff and we can neglect it in some cases, we can consider the blade to have purely flap lag type of motion. And in that case, the torsion mode can be considered separately. Now, the Coriolis force we will see couples the flap and lag motion, and this is pretty strong coupling. So let's look at the free body diagram first for the flap motion, and then we are going to look at it for the lag motion. But one of the things which is happening here is that the lag term comes into the flap equation. So if we look at our usual flapping blade, the offset E here, there's a spring force. Now you recall from our previous discussions there is going to be a centrifugal force here, an inertia force here, and aerodynamic force here. Now the new component is this Coriolis force, and this Coriolis force acts because there is a velocity r minus e zeta dot which is opposite to the direction of rotation, and therefore the Coriolis force is going in, and it has the equation twice into the mass of this small segment, that is mdr, into rotation into zeta dot r minus e zeta dot being the velocity. Okay, now that's the component of the lag motion into the flap equation. We'll explain that in the next slide how this velocity comes, but let's look at one more velocity term which comes from the flap equation. So now in the flap we see that there is a component here beta dot r minus e which acts in this direction. And so if we take a component in this direction here, that's going to be beta dot r minus e into beta. Okay, so that's the component in this direction, and therefore that component is going to come in the lag equation. So we are going to look at this beta dot r minus e beta in the lag equation in the next slide. So now we look at the lagging blade. Again, usual forces are there, but what we are interested in now is the Coriolis force. So let's first see the term which we used in the previous lecture or previous slide, and that term was r minus e zeta dot. And you can see this r minus e zeta dot is simply because of the motion of the blade here, so it comes from zeta, and this is the velocity in this direction, and because the velocity is in this direction, an invert Coriolis force is acting in the flap direction. Okay, now as far as the lag equation is concerned, here your flap term is going to come in. So if you remember, the flap term was beta dot beta r minus e, and this is the velocity at mass mdr. So this is going to also lead to a Coriolis force, and this force is going to be in the direction of rotation. So here the direction of this Coriolis force is in this direction. So let's now summarize these forces, and then we are going to write the governing equation for the flap lag problem. So let's start with the IF, and here you have your usual term m r minus e beta dot dr, and the arm is r minus e about the flap hinge. For centrifugal force, you have our usual term here. We recall all these terms are same as it was in the pure flap equation when lag was not there. Same with the AF, the aerodynamic force, and the spring force also. Now what's new is this Coriolis force term, and essentially this term is 2m into the velocity r minus e zeta dot into the rotation speed into dr, and the arm is going to be r minus e beta. That's the arm of this Coriolis force term. So it's similar to the arm of the centrifugal force term. Looking at the lag mode forces now, we again get the same type of equation for the IF, the CF, the AF, and the spring force. So here you have the inertia force m r minus e zeta double dot, arm r minus e about lag hinge. You have the centrifugal force, you have the arm here, and so on. Now what is new is this Coriolis term, and here you can see it is twice into the mass, which is mdr, into the velocity, which is r minus e beta beta double dot, and then you have the rotation speed term, and here this has arm of r minus e. So here the arm is the same as the arm for the IF, or the inertial force. So what we see now is that there are these two new Coriolis terms. And why are these terms coming? Well, let's look at the term in the flap equation. Now the mass m moves inwards with a velocity r minus e zeta dot, and therefore it produces this term here. In the lag mode, the mass moves in the direction of rotation with a velocity beta dot r minus e beta, and therefore we get this Coriolis term here. Now if you are slightly confused at this point, you can go back to my previous lecture and look at the particular situation where we had constructed a problem of a disk and a person walking on the disk, and essentially we realized that if this person walks toward the center of the disk, or he walks circumferentially, Coriolis forces get created. So the same thing is happening here. The mass is moving towards the center, or it is moving in the direction of rotation, and these are going to lead to these Coriolis force terms being there. So let's now take the moments, and the moment first we take about the flap hinge, so we get the flap equation. So that's our flap equation. So this integral is from e to r because we are taking the moment at the hinge. Okay, and all the terms you have seen before in the derivation of the flap equation, you can go back and check that lecture. Now the new term is this zeta dot term, and that's the Coriolis term here. Okay, and when you simplify this equation, you get this term here. So that's the new term involving zeta dot. And very interestingly, this has a zeta dot beta here also. So it is effectively a nonlinear term. Our usual nomenclature is here again. You have nu beta, which is the flap frequency, and you have the non-rotating flap frequency. Okay. Let's do the same thing with the lag equation. So we take the moments at the lag hinge. Like I mentioned before, we are assuming the flap and lag hinge to be at the same location. So this E value is the same in the flap equation and in the lag equation. And then we expand this out. Now you will recall the zeta double dot term is the same as in the lag equation before. You have a centrifugal type of term depending on the square of the rotation speed, and you have this new term here which is due to the Coriolis force. So again, this is a nonlinear term, and one of the ways you can find out the Coriolis force term is that you will find one rotation speed here, and typically it will be in the form 2 into mass into rotation speed, and that's the spring force term. So again, you can simplify this equation in this form if we take I zeta and extract it out. Okay, recall that I zeta would be the integral of this. So these integrals can be obtained if you know the mass distribution. So here, of course, remember that m is the mass per unit length. So now nu zeta will give you this frequency. That's the frequency in lag. So we can simplify these equations further by dividing the flap and the lag equation by IB into rotation speed square, and we also make certain approximations here to clean up the equation. So the clean equation looks like this. Now why we like to clean this is that it puts it in a pure mathematical form. And now you recall the previous equation, we essentially had a spring and a mass system. Okay, so both for the flap and the lag, the spring terms involve the nu beta and the nu zeta respectively, and the mass terms are the double star terms here. There was a forcing on the right hand side which effectively came from the fluid mechanics of the problem. Now, what is interesting is the presence of these two terms here, and if you look carefully, you can spend a lot of time staring at this equation, and this equation after some time will start talking back to you. And one thing it's going to tell you is that this is not an easy equation to solve because these are nonlinear terms. So you straight away see here that even for a simple problem, relatively simple problem, we are encountering quite strong nonlinearities here. And like I mentioned before, these m zeta and m beta are essentially manifestations of the lift drag on the blade section and so on. So these are essentially coming from the forcing. So we see that the flap lag equations are coupled through Coriolis force terms. Also, we see that these are nonlinear differential equations, and that's something very important which we see in helicopter dynamics, is that even for relatively simple problem, we encounter nonlinear differential equation. Now, for a rotating blade, this strong nonlinearity cannot be neglected. Sometimes people who work in fixed wing or other problem, they look at nonlinearity if your deflections are large. Okay, and therefore that's a very specialized problem. But as far as helicopters are concerned, this nonlinearity is going to be present in all cases because it's part of the physics of the system, and so you cannot get rid of it. You need to figure out some way to solve this nonlinear system. And as you can expect, the solution of such equations is quite a difficult problem. These equations are difficult to solve, though there are various methods in nonlinear differential equation theory which you can actually use to solve them. So one of them would be to linearize these equations around a particular given state. So first you could obtain a solution of these equations by setting aside the nonlinearity. So essentially get a linear solution and then use a Newton-Raphson procedure of piecewise linearization and solve these equations as time goes forward. So that is my take on the flap lag equation. I will see you in a new video in the next lecture. See you then.